tell us about her thesis research on a one-dimensional model for the pulsating flow of cerebrospinal fluid in the spinal canal. Stephanie?
Thank you, Dr. McCulloch. Okay, so yes, as he mentioned, today I'll be discussing the work actually we recently submitted on a model for a 1D model for the flow along the spinal canal. If now it will go, okay. So some of you may already know this, but CSF, or cerebrospinal fluid, is a colorless, odorless fluid that bathes the central nervous system, including the brain and spinal cord. It also sits in the cavities of the brain, which are shown here. You have your lateral ventricles, third and fourth, connected by the cerebral aqueduct. I don't know how my audio is, but I just got a pop-up from Zoom. Do I sound okay?
I think you can.
Oh, okay. It's okay. It's considered a Newtonian fluid with properties of water at 37 degrees Celsius, including viscosity and density. And we also know that it serves a dual mechanical and physiological role in the body, where mechanically it serves like a shock absorber for the brain, and physiologically it circulates nutrients, removes metabolic waste, maintains our ICP. So we're interested in the flow along the canal, so it's important to recognize that the central nervous system is comprised of two compartments. You have your spinal canal and your cranium, which is a rigid container that contains your blood, CSF, and brain tissue. And so the flow along the spinal canal is pulsatile, with when the blood flows in and out of this rigid container, right? So the blood flowing in and out causes the intracranial pressure to actually fluctuate with each heartbeat. And this is to ensure that the sum of the volumes inside this rigid container remains constant. And in the medical community, this is actually known as the Monroe-Kelly doctrine. It's also important to realize along the canal that we also have like additional anatomical features, right? So you have these extending nerve roots from the spinal cord. And you also have what's called tuberculi, which are like these web-like collagen protrusions that connect across the subarachnoid space. And here's where like the cerebrospinal fluid will sit. So we have actually already measured the flow rate of the cerebrospinal fluid along the spinal canal previously. What we're interested in, that's what's shown in this figure here, but what we're particularly interested in is this observed phase lag and amplitude decay of the flow rate along the canal. So we're trying to model this with the simplest model. We're fortunate enough to be able to do this through MRI. So we have anatomic scans that allows us to obtain the geometry of the canal, which is shown on the left. And then on the right-hand side, you have our phase contrast images, which allows us to quantify the flow rate along the canal. The phase contrast, for those who may be more familiar with MRI, we made sure that the velocity encoding value or the Vang value was high enough to where aliasing in these images didn't occur. So basically it had to be adjusted as we went along the canal. It's also important, there are some additional considerations that we need to make when modeling the flow along the canal. One of them being the intracranial pressure, which fluctuates at an angular frequency of the heart rate and an amplitude delta P. The angular frequency corresponding to about 2 pi for 60 beats per minute. And on average for a healthy individual, amplitude of 200 pascals. This intracranial pressure drives a small amount of fluid in and out of this, in and out of that rigid container, like in comparison to the total volume of the canal is much smaller. So so this delta V, this small stroke volume in comparison to the total volume of the spinal canal. The average cross-sectional area is very small. So the square root of it indicates that our problem is actually slender in comparison to the total length, which is approximately 60 centimeters for an individual. The characteristic streamwise velocity then is on the order of 10 centimeters per second. Our corresponding Struhal number, which is the ratio of the local acceleration to convective, indicates that our problem is linear. So for those who have taken, fluid mechanics class, have your nonlinear term from the convective acceleration. So basically, our problem is linear. We also know that along the canal, it deforms very small. So the change in cross-sectional area is very small as a result of actually that small stroke volume in comparison to the total volume. And we're also for just to be as simple as possible, we're just going to assume that the spinal canal is linearly elastic with a function gamma, which is our compliance that can vary along the canal. So we begin with just assuming that the flow is inviscid, or we're neglecting viscous forces. So when we go ahead and follow through with continuity and the momentum, we start with continuity here, and we integrate over the cross-sectional area to get the relationship between the flow rate and area. And when we substitute this into our linear elastic equation, we get our first expression relating the flow rate and pressure. Our second expression comes from the longitudinal momentum along the canal, which again, we're integrating over the cross-sectional area. So it's our second expression. Of course, we have our boundary conditions, right? At the end of the canal, there's going to be zero flow rate, and then the entrance, we have our ICP. And we can combine these expressions to obtain a wave equation, basically, in terms of either the pressure or the flow rate, which is dictated by an elastic wave speed c, which depends on a characteristic compliance value and our average cross-sectional area. I won't necessarily go into the details of the value of this characteristic compliance. I'll discuss it a little later, but for now, when we substitute that in, we get an elastic wave speed that is on the order of a few meters per second, which is actually consistent with what we found in other reports. So this looks great, right, until we apply a simple case where the ICP is a simple cosine wave. So when we follow through with the math, we obtain our expression for the pressure along the canal, which is dictated by this, or you have this K value, which is just a dimensionless parameter that has the length and the wavelength. And then you have our flow rate. And when you substitute this in, of course, you find quickly that there is no phase lag in this case, right? So it actually oscillates in phase throughout the entirety of the canal. So we have to reevaluate what we're doing, right? So in order to, our guess is that the phase lag induced along the canal is from viscous forces. So now we're going to incorporate viscous forces, right? So we're going to incorporate the shear boundary layer along the spinal canal, which is dictated by our Wamserli number. And also, as I was talking about earlier, we have these anatomic features or trabeculae that we're going to assume basically instead of having an open canal, we have like a porous media. So for the pressure loss, we'll just use Darcy's law. So now we'll go completely dimensionless, right? So I have here a list of all of our variables and corresponding scaling factors to make them dimensionless. And then for sanity's sake, I'm just going to remove the asterisk notation. So from now on, it's dimensionless. Anyways, besides the math is not so important, it's more so that you see that we have, again, our continuity and linear elastic expression, but then the difference comes into our longitudinal momentum equation, where now on the right-hand side, we have the shear viscous stresses and our resistance induced by the trabeculae. And this resistance is a function along the canal, or can be, which is dictated by, the permeability, or kappa in this case, and our viscosity and angular frequency. So this is where I'm going to skip through a lot of the math, but basically we can, solve that by substituting in Fourier expressions for our ICP. And then when we follow through and substitute in, we have an expression or a boundary value problem in terms of the coefficient of the flow rate for the Fourier series. So we can take these coefficients and reconstruct. And again, like I was saying, we have our resistance term here and shear stresses. So we went ahead and did this actually for a couple subjects. And here I'll just show the results for one. But again, like I kind of already showed you a figure similar to this. But this is just, again, we have, the spinal canal and the corresponding, coordinates and the cross-sectional area. So these are MRI scans, right? And this is an axial view. So if you slice through, and then this is just an illustration showing kind of what the trabeculae look like. And then our corresponding cross-sectional area, which is dimensionless in terms of the average cross-sectional area, and our perimeter. So the perimeter is going to also change as it goes down, because at one point the spinal cord ends. And one thing that is important to recognize too, there are continuous nerve roots down here, but for our case, we're just going to completely end it here. The nerve roots are, I think, what they call basically cortex tail at the sacral end of your spinal canal. But then so now we have the geometry of the canal, right, for our model, and we also need the intracranial pressure. Of course, for a healthy individual, we cannot, morally stick in a pressure sensor to, measure real-time intracranial pressure. So what we did was we just took from the literature a characteristic waveform that has been measured. It's important to know that for the ICP, typically for a healthy individual, you have like these descending peaks. So that's just what we did initially. Of course, ideally, it would be nice to be able to utilize a real-time same subject. But anyways, so that's just to begin with. And then, of course, we have our other parameters, such as our heart rate, the length of the canal, our average cross-sectional area, and our Walms-Rayleigh number. Okay, so this plot I know is a little busy. We added to it. Didn't think it was necessary, but if you focus on the left-hand side, right? So here's our MRI measurements and the corresponding locations along the canal. And then you have here our model, which we're substituting in a value for R of 4.78. And this value actually corresponds to, basically comes from our understanding of like the porosity or permeability of the spinal canal based off of other reports. So this was an estimate based off of other reports, basically. And then we have the case where R is 0 and a couple of different ranges of values for R. Clearly, when we neglect this resistance induced by the trabeculae, like the waveform clearly does not correspond at all to what we measure, right? You have like essentially like two peaks in the waveform. And then over here on the right-hand side, we have the stroke volume, which corresponds to basically half of the absolute value of the flow rate integrated over the, the heart rate. And so of course, like, it should be the largest at the top and then it should get to 0 at the end of the canal. So the dots correspond to the MRI measurements and then the lines to different values of R. So clearly, like R on the order of unity, it corresponds close, like closer to what we measure than anything else. So, and I guess I went a lot faster than I anticipated. But basically, the key takeaway here is that with this simple 1D model, we're able to recapture the CSF dynamics that we observe along the spinal canal. And one of the more important observations being that we actually do need to incorporate these microanatomy features, or like the trabeculae, in order to actually capture that phase lag that we see. And the phase lag, and also the attenuation, the rate of attenuation. Like I said, we recently submitted this, and of course, like we have like a lot of future work that we're looking forward to for continuing this modeling effort, where we're going to, optimize these parameters for an individual subject. So ideally, we'll have like a range of subjects to measure. And of course, as I mentioned, that resistance term, we just assumed it to be constant, but that can vary along the canal. So it would be interesting to also like maybe in a we could optimize it in a conventional manner of just a simple optimization problem with assuming that the compliance and the resistance are constant. But we could also, take a step forward and try and optimize it for functions along the canal. There aren't many, or if not any, reports that actually indicate the change along the canal. And so that makes it a challenge. If we had enough subjects and data, we would be able to, do some kind of like machine learning maybe. The other thing we want to do is, be able to understand because what I did was, as I was mentioned, let me just go back. So we use like a healthy characteristic waveform for the ICP, but of course, what we're down the line trying to do would be kind of the inverse problem, where we're able to take the flow rate along the canal. So this is of course non-invasive, right? MRI is non-invasive. Take those measurements and then be able to, estimate the ICP as a result of that. And through the ICP, of course, you can determine whether or not there are certain disease cases related to variations of the morphology of the ICP. So it would be ideal to kind of be able to do the inverse problem. And so understanding the relationship, between the variation of the ICP and the flow rate is something else we're looking into. So with that, I'd like to, give all of the appropriate acknowledgements. And lastly, I'd like to dedicate this presentation to Professor Wanda Sharis, whom I believe quite a few of you knew. He passed away actually this time last year from cancer. But without him today, I wouldn't be here giving this talk. He was very firm about me joining interfaces. So he's the reason I'm here. And with that, I would like to open for questions.
Can I go ahead? That was really cool. So my question is kind of about the resistance term, and in terms of like healthier cases versus diseased cases. Would you expect that after some kind of traumatic injury, the resistance would increase? And like, how would you account for that? Or what kind of like eventual modeling would you want to do with like, you kind of talked about this at the end, kind of doing the reverse problem, but I'm just kind of curious about like spinal injuries and how that would affect resistance.
Yeah, that's a good question. I'm not entirely sure. I don't know if in disease cases there are actually changes in the trabeculae, for example. There are disease cases that affect, for example, the geometry. I know because that, well, of course, like, what's the spinal deformity? Why am I scoliosis? Yeah, scoliosis, for example, or even in flow related, which is like syringomyelia, which is like when a pocket of CSF fills like the internal cavity of the spinal cord. So the cord actually enlarges slightly, or even, you know, a herniated disc, for example, that's going to, of course, affect the flow. Like all of those things, yeah, of course, like if I had infinite resources and subjects, I would go down the line. I'm not entirely sure.
Okay, nice. Yeah, that makes sense. Yeah, great job.
Thank you.
Yeah, thank you, Stephanie. That was very, very nice. And thank you for remembering Dr. Lacheris too. He was really a great mentor to a lot of students and also to a lot of our junior faculty. I like that your analysis basically at one scale revealed the importance of structure at another scale. And so I was wondering what thoughts you had about like more explicitly studying that trabecular structure and incorporating it into say models that go to that next scale of organization.
Yeah, I mean, it would be amazing to be able to, because honestly, yeah, there really isn't much reports on it. I think the average transverse size of the trabecular on the order of like half of a micron or so. But I mean, I don't know if, I mean, I wouldn't even know where to begin to be able to do that kind of investigation.
So there are sort of region of interest type of homogenization strategies that people have used.
Mhm.
So where you choose a smaller region and a higher resolution image, and you make essentially a high resolution model of just that small region. And in this case, I think, you know, basically could just be a drag model.
Mm-hmm. Yeah.
And then you could take all that result and you can incorporate it, even for different structures, into your macroscopic analysis. And so using some sort of homogenization or mixture approach. But where they sometimes call them representative element methods or region of interest analyses, where the scale down is too fine to represent for the entire structure, but where in any case, it's more like this sort of aggregate effect than, like, you're not really asking how the flow around some particular trabeculi is different from around another, but how their presence in general affects the flow. And then how maybe differences, now maybe there are differences along the spinal canal, or maybe the differences between patients or differences with disease, how those differences might affect result. But you don't really need to explicitly model every trabecula in order to be able to sort of predict.
Yeah, I haven't even, yeah, that's something I haven't considered before. So thank you. Yeah, I will look into that.
Any other questions for Stephanie?
Yeah, I had a quick one. This kind of actually is a little bit related to what Professor McCulloch just talked about. I was going to ask if you think there's any value in doing a 2D or 3D simulation of your model, like looking at different structure features, I guess.
There has been a couple studies. So the only issue is, I think one of the things or goals we try to do in all of this is make it so that it's like clinically accessible, right? Because a lot of CFD simulations and stuff, like doctors and clinicians aren't going to run 48-hour like 3D simulation to get results about their patient, right? So if we had some kind of metric or so that's like a doctor's dream, right? Is just to have like a single metric that says disease, no disease, basically, right? And I think that's kind of like where we're trying to head with this, especially with the ICP relationship. So yeah, I don't know if for what we're trying to do that would be worth it or not, but it's definitely something like we always discuss. And
yeah, I think patient specific. Sorry, there's an echo. Being able to do patient specific modeling would be really cool.
I And so actually, I think that what came to my mind is the official name of that method is called representative volume element method. So and they may use it more for solid mechanics, but I can't see why in principle you couldn't use it for fluids either. It's a more or fluids direction. Well, congratulations again. Thank you everyone for coming. And I guess maybe next time we'll be hearing from Sean.
Yeah, probably. That'd be good.
Fantastic. Okay. Thank you very much, everyone. Thank you, Kelly.
Thank you.
Thank you, Stephanie. Bye-bye. Thank you.
Bye. Thank you.